Passive decay drags on for seasons, but engineering the exact biological conditions reduces inert organic matter into rich soil in days. Most autumn yard work ends by dragging dead leaves into a massive pile and waiting for spring. However, aggregating organic material into a static corner does not yield efficient decomposition. As winter rain saturates the pile, the sheer weight of wet organic matter compresses the layers flat. This physical compression crushes the empty space between the leaves, eliminating the oxygen that soil bacteria require to survive. When microbes suffocate, biological breakdown stalls. This failure state is known as anaerobic stasis, a condition where leaves pickle in a cold, stagnant sleep rather than rotting. We can bypass this anaerobic stasis and ignite a high-heat aerobic cycle by managing the pile as a biological engine. To run that engine smoothly, you must strictly control 3 parameters: the mechanical surface area of the fuel, the chemical balance of the carbon-to-nitrogen ratio, and the thermodynamic mass of the pile. Regulating these 3 variables allows you to compress a passive 18-month wait into an aggressive 18-day active biological cycle. Achieving independent fertility for a farm or garden requires precision biological engineering. A senesced brown leaf is essentially packaging. Trees engineer that packaging specifically to repel moisture throughout the winter. The exterior surface of every leaf is coated in a waxy cuticle. This hydrophobic layer evolved to shed rain and protect the plant's internal structures. This diagram shows a cross-section of stacked whole leaves. The overlapping flat shapes act like tiny shingles, deflecting moisture outward. This shingle architecture creates a localized environment that remains completely dry, locking out the moisture and microbial access required for decomposition. To initiate aerobic composting, you have to break that architecture. Mechanical disruption, specifically running a lawnmower over the material to shred it, is a non-negotiable physical prerequisite. Shredding physically destroys the waxy cuticle, dismantling the leaf's evolutionary defense mechanisms. Mathematically, crushing that whole leaf into confetti yields an exponential increase in the surface area to volume ratio. The structural change transforms the material into a hydrophilic sponge, allowing internal tissues to drink in liquid rather than shedding it. Millions of freshly torn edges and open veins provide the necessary entry vectors. You are cutting the carbon down to size, allowing initial bacterial colonies to crawl directly inside the tissue and feed. Physical architecture dictates biological access. Without mechanical disruption, the essential chemical reactions simply cannot begin. Soil microbes require 2 fundamental building blocks to thrive. Carbon serves as the energy fuel, while nitrogen provides the protein required to synthesize new cells and multiply. Fallen leaves consist almost entirely of carbon. A pile of dry yard waste naturally sits at a ratio of about 80 parts carbon to 1 part nitrogen. This severe nitrogen deficiency creates a carbon lock. The environment is so heavily dominant in carbon that microbial populations exhaust their available protein and stall. To trigger rapid biological replication, we have to pull that ratio down. The optimal target for high-speed aerobic decomposition is 30:1. A common misconception is that you can balance this ratio simply by broadcasting dry nitrogen powder or lawn fertilizer over the top of the pile. This diagram illustrates the physical failure of dry applications. Gravity pulls the fine nitrogen granules straight down through the loose carbon matrix, settling on the soil floor. This separates the catalyst from the fuel, leaving upper layers starved of protein. Breaking the carbon lock requires applying a liquid nitrogen suspension, such as blood meal or manure tea. A liquid carrier ignores gravity's sifting effect. As it pours over the shredded leaves, the liquid coats the expanded surface area, achieving uniform saturation throughout the matrix. This delivers a dual-action benefit. It provides critical hydration to the desiccated plant matter while depositing nitrogen directly onto the cellular sites where bacteria are waiting. Utilizing a fresh manure suspension offers an additional biological advantage. It inoculates the pile with an active starter culture of living gut biome bacteria, accelerating the initial breakdown. Escaping the carbon lock demands a liquid delivery vector to physically fuse the biological catalyst to the fuel. The final parameter required to run the engine is thermodynamic mass. This visual model highlights the minimum volume needed to generate heat, a 3-foot cube. The exterior insulates, trapping metabolic heat generated by bacterial respiration deep within the core. Built correctly, the core crosses the thermophilic threshold, reaching 150 degrees Fahrenheit in 72 hours. Hitting this specific temperature band neutralizes dormant weed seeds and destroys harmful plant pathogens. Around day 5, the core temperature will begin to drop. It is easy to assume this thermal decline means the biological fuel has been exhausted. The true cause is localized hypoxia. The massive bacterial population at the center has depleted the available oxygen in the core. Mechanical inversion is the necessary corrective action to rescue the aerobic process. Aggressive physical churn forces the cool, uncomposted outer edges directly into the steaming center, reoxygenating the entire mass. Flipping the pile inside out moves the insulated exterior into the core while introducing a spike of atmospheric oxygen. This oxygen influx restarts aerobic metabolism, driving core temperatures back up to the thermophilic threshold. Managing compost temperature is an exercise in managing oxygen. The pile operates as a breathing biological engine that requires manual intervention to avoid choking. This chart plots the 18-day thermodynamic life cycle. The jagged line maps the engine's rhythm, rapid heating, localized hypoxia, and recovery driven by mechanical reoxygenation. By day 18, the temperature curve permanently flatlines, indicating thermophilic bacteria have fully exhausted the readily accessible energy. The system now transitions into its final metabolic phase, handing the workload over to fungi and macroorganisms to cure and stabilize the material. The output of this cycle is a mature biological asset, dark, crumbly humus ready for application. Mastering this 18-day cycle allows a farm to replace commercial soils with organic matter processed on-site. The process improves soil structure, increases local biological diversity, and reduces annual input costs. Thanks for watching. If you want to see more content like this, make sure to subscribe. Understanding the rigid science of decomposition transforms an agricultural liability into biological wealth.